When I started getting into rocketry, one of the things that really confused me was that the physical size of an engine didn't always correspond to how much thrust that engine would produce. It gets really crazy. Like, in some cases, an engine that's half the size might produce up to 5 times as much thrust. So what's going on here? To really understand why certain rockets have more thrust than others, we first need to understand really how rocket nozzles work. The big difference in size between the two liquid rockets that we're showing as examples here is basically the rocket nozzle, or the bell that is coming off the rocket part. But understanding how these rocket nozzles are kind of exploiting the rules of physics is actually really interesting, and will provide some insight to us as to why the size of a nozzle doesn't necessarily correspond to how powerful it will be. So why do we even have these nozzles in the first place? Well, essentially what we want to do with a rocket nozzle is somehow convert the explosive energy of our rocket propellants into a nice controlled reaction that will take us somewhere or provide forward movement. So the first thing we want to do is we want to take the explosion that's happening inside of the combustion chamber, and we want to direct that flow to the bottom of the rocket so that we produce thrust that goes in the opposite direction. This is essentially Newton's third law, which is that for every force that goes one way, there's going to be an equal force that goes the other way. And that's kind of basically how rockets work. Not too complicated.
That was easy.
Of course, the key to making a good rocket is making sure that the force that's going in the opposite direction is as big as possible, so we get as much force going forward as we possibly can. There are two ways that we can increase the force in which we're producing in the opposite direction. One is just to make the reaction such that there's more mass that's going out the other end of the rocket. Of course, this is nice, but the problem is that we need more fuel in order to do that, so it's not necessarily the most efficient. The better way to get more thrust is actually to increase the velocity of the gas as it's leaving the combustion chamber. This way we get more push, but we don't have to use more fuel. So how do we do that? Well, it turns out that this problem was actually being worked on by physicists during the 1700s. If you restrict the orifice of a flow conduit, you can actually get the fluid velocity to increase. This means that as we make the combustion chamber opening smaller and smaller and smaller, the velocity of the gas coming out of the combustion chamber should get faster, faster, and faster. This is a really cool principle, which means that we can just basically tailor the geometry of the exit of the combustion chamber such that we can get a really fast exhaust flow rate. So it seems like if we just make this nozzle smaller and smaller and smaller and smaller, we could make it like super really tiny small, and we'd have the most thrust we could possibly get with a really fast exhaust flow rate.
That doesn't make sense.
But it turns out it's actually a bit more complicated than that. Unfortunately, we can't just infinitely restrict the whole diameter that comes out of the combustion chamber. We actually run into a problem that's called choked flow. Essentially, if the flow velocity of the combustion chamber gases get so fast that they reach the speed of sound, it's actually impossible to accelerate them any further. So if you keep restricting the diameter smaller and smaller, you won't get any faster flow. And you're just reducing the amount of mass that's going through the nozzle, and you're actually making it produce less thrust. So that's not very useful. In order to get around this restriction, there's actually some more interesting physics that happen inside of the flow of the exhaust gases. It turns out that when you get to the state of choked flow, you can actually keep accelerating those gases by doing exactly the opposite. Instead of restricting the diameter, you can actually increase the diameter, and they'll start to go faster and faster and faster. It's almost like the rules of physics kind of flip on their head when we get to this choked flow condition.
Nice.
So essentially, in order to have an efficient working rocket, which has flow velocities that leave the combustion chamber as fast as possible, you first want to restrict the flow until we get to this choked flow condition, and the exhaust is moving at the speed of sound. And then you actually want to expand the opening in order to keep accelerating those gases faster and faster and faster into the supersonic speeds. And this is how we kind of get this hourglass look for rocket nozzles. And that's kind of what we see in the rockets today. So by this logic, wouldn't we just want to expand that nozzle as much as possible in order to get the highest possible velocities that we can? Well, it turns out that in the vacuum of outer space, that's the way we want to do it. The more expansion you can get, the faster those gases will be going, and the more efficient your rocket nozzle will be. Of course, you don't want to make it too big, because then you kind of are taking a lot of mass with you, and then you kind of get diminishing returns. But there's one more problem that we haven't talked about, which is actually one of the atmosphere. So we happen to live on Earth where there's kind of a thick atmosphere that's all around us. And when you expand the nozzle as you go away from the throat, which is that restriction point, the pressure inside of the exhaust gas gets lower and lower and lower. But there's a problem that comes if you try to lower the pressure of those gases too low. So if you go less than the ambient pressure around you, you actually end up getting negative thrust. Because the pressure inside of the exhaust is not very high, the atmospheric pressure actually pushes in on the flow plume, which causes your engine to kind of lose thrust. And also it can get dangerous because if there is really not enough pressure inside of the exhaust gases, the atmosphere can actually go into your nozzle and it can create lots of weird instability conditions, which can sometimes just tear the nozzle right apart. Not really that good. So in order to get around this problem, we can't really make our sea level engines, or the ones that are going to be operating inside of the atmosphere, very big in terms of the nozzle diameter, because otherwise we will end up probably breaking our rockets. But this kind of sucks, because the rockets that we want to be the most powerful are the ones that have to take off from the ground, because they have the most mass to push up and get into space, right? So because of this, we kind of end up getting these smallerish looking rockets, which go onto the start of a booster stage that lifts off from the ground. And then we get this giant rocket nozzle that goes onto the second stage, which is only going to fly in space. In space, there's no air, so you can kind of make that nozzle as big as you want, and you'll never run into the situation where the atmosphere is like pushing back in on the exhaust gases. So that's the physics of why in rocket science, bigger is not always better. If you want to learn more about rocketry with us, be sure to give a like. And remember to keep expanding your horizons.